Hey, welcome to part 6 of this series of implementing a virtual console using web technologies and an AI assistant to help accelerate the process. In this episode, we're going to focus on getting some graphics on the screen, which hopefully is quite exciting. It will be pretty basic to begin with. I've got an interesting demo I'll try at the end. It may not work, we'll see. If it doesn't work, I'll probably go offline, hit it with a hammer a few times, and then come back online and sort of skip the time because we'll see when we get there. So focus on rendering. I've made a few changes since the last episode just to essentially do some basic refactors. So if you look at the browser now, I've inputted a tab view, and that's so we can excitingly show our console. That's just a canvas element at the moment, it's not doing anything. Then in the code, I have essentially pulled things around a little bit. I refactored I think it's tab strip, panel, and did I do this episode? I did these last episode, didn't I? So I've introduced the tab strip. That's all I did between these episodes. But I did do some work on the specs. So one of the things I was looking at in readiness for rendering was the video specs. I'd made a real mess of in the memory layout rather. I'd made a real mess of the frame buffers. Let's find it. The frame buffer. I had written this so it talked about the memory going downwards, which was really confusing, and as a result all these addresses had gone wrong, and I can't remember. I definitely remember writing the downwards bit. I don't know what I was thinking because it was a really bad way of phrasing what I meant. What I meant is the memory space ends at 0xFFFF, and our start of memory is some way before that. And I'd written it in a very esoteric fashion, which you could dig out in the Git history if you like. As a consequence, all the addresses were out on here, but I also decided to make it more clear what the coordinate system was. So top left is 0, 0, bottom right is the sort of max width, max height of each resolution. So I tidied that up. Video.md, I've done a little bit of just rejigging to make this clearer as to what the palettes are, and I introduced this palette indices section. That's our sort of default palette for the 4 bits per pixel mode, 16 colours, and I converted. I think this was in OK CLH format. I can never remember what the actual that is. From Tailwind, I got that converted to RGB formats. In my last row, I got the offsets wrong, so I've just cleared up that a little bit. So I fixed it. I fixed up those specs in readiness for doing this rendering work, and while I was working on 2 new specs, I decided to do these in advance, so that hopefully this will just take an hour. But we'll see. Obviously, the last episode was rather long. Set up palette.md. If you look in the memory layout, let's find palettes. It's probably going to be up, maybe it's down, up, scanline palette map and palettes. So our palettes are indexed palettes. So for 4 bits per pixel, each kind of colour that we'll set 0 to 16, and it's an index into our full palette, that big palette we have. For 8 bits per pixel, it's still an index, but it's just lets us rearrange the colour order. That'll let us do some fun tricks later on, I hope. And the other thing we've got is for each scan line on the screen, you can change the palette that's in use. Obviously, you can't really do that for the 256 palette because it takes all the palette space. Sorry, no, it doesn't. You've got 4 palettes. I forgot. I originally just had one palette for 256 colours, but I rearranged it, so I gave it some more space. So you can have 4 different arrangements of a palette. For 256 colours. That'll let you do some of the sort of fun cycle effects that you used to see on the 8 bits, and that has made me realise that my setup palette, I've talked about 16 palettes. Here, one second, we'll come to this in a second. As per the spec. Yeah, so that's our palette kind of stuff. I'm just trying to make this super clear. And so that's our palette stuff. And what I want to do is create a new file called palette in the console directory that lets us sort of manage a palette, because we'll probably do more things with it later. Sets the default screen mode in the video mode register. So again, if we just go back to the top, we've got a bunch of hardware registers in the sort of low memory bound. One is video mode, which lets us select one of our 4 modes. I may end up, depending on how many of these things we add, I may end up compressing some of these. That's obviously using 4 bits, so we could put another 4-bit flag in there. We don't have another 4-bit flag at the moment, but we'll keep an eye on that kind of thing. Yes, so that's part 1, and that's what we'll do first. Yes, and this should, when the CPU is started or reset, it's going to set mode 0 as the default and reset all the palettes back to default. So I'm going to give this a go in Claude now. Where are my specs? Read specs / implementation / setup _ palette.md. Oh, I've used underscores here and I'm using dashes for the others. I don't know what's happened there. I'll fix those before I commit it. It's early in the morning here. I woke up very early, so I thought I'd crack on with this. It's probably rattling around in my brain every night because it's quite interesting. Okay. If any of these Claude become long and boring, I will skip them like I have in an early episode, and we can rejoin at the end, but we'll see how it goes. I don't think this one will be too bad, but I think the next one might take it quite a while, and we'll look at that in a second. That's Rafi. There's somebody outside, mate. Probably someone going to work. Have a temerity within 100 metres of a house. Taking it longer than I thought. Let's see what the thinking's doing. Seems to be stuck. Yeah, I think I've probably got, I don't know, I guess Claude throttling or something. Yes, you can create palette.ts. Maybe everybody else is working on their virtual consoles at 6:30 in the morning. Yes, you can do those things. So we should be able to see this in our memory map. The palette, I think, is at 0x200. So we should be able to see this stuff in a memory map when it's finished. I'm just going to make its edits because I've got my commit as a rollback point as per usual. So what we should see in the palette index space is the same sort of repeating 2 rows. From a hex view, we've got 8 bytes per row, the 16 indexes, so we should see 2 rows of data. Pardon me, of data repeated many times. But let's have a look. So let's go to the browser. If we were to put 200 in, I might need to run it to see it. No, okay, so we're not seeing anything. That's not good. Oh, there we are. Sorry, yes, there we are. It's obviously it's not started to begin with. That might be an improvement to make, is to kind of preload the memory map, as it's going to be really confusing just to see an empty memory space before you press run. But you can see we've got the same repeating 2 rows of data. We'll have that many times because there's a whole K of those. There are 64 different palettes. Which is probably a little bit egregious, but I needed some space for the 4 palettes for 256. There's nothing stopping you as a developer using some of that palette space for your own data. It's just that the system will look at that space if we tell it to look at that palette index. So you could stuff some code in there, stuff some variables in there, and many, on the 8 bits, memory is always a challenge, so people would do that all the time with these systems. So great, it looks like it's integrated our palettes. It looks approximately right. FD, that's black in the palette index, that's white. So yeah, that looks correct to me. We let it run on, so it's interpreted, because I pressed run, it's moved a program counter on, and it's now in here thinking this is code. Obviously it's not code. That won't work very well. And we need to start pushing our org back to a more realistic value. I have defined where user space starts. Let's have a look at that. Memory layout. General RAM, B80, 0x0 B80. So if we were to go into our editor container, look at our default program, this ought to be B80. Go into here, reset that, B80. That should now, when we assemble it, load into memory here, safely out of the way of the other things. Great, so can't see anything yet, but we've got some palettes. Just add this stuff. We ought to have a quick look at the code. We saw what it did in the CPU. That was really simple, and it added a line where I expected. Let's have a quick look at the palette setup code. There we go. Okay, video mode register, palette map start, scan up palette, fine. We didn't look at the scan lines in the memory map. We ought to look at that. They should all be zeros though, because I've just said set all those to 0, but set video mode. There's our default 4-bit per pixel palette. It's pulled that from the spec. Good. Initializing a palette based on the mode. Okay, fine. That looks correct, and we know it's right because we've seen it, so that's good. But yeah, it's just doing what we would expect there. And then the 8-bit per pixel, yeah, just writes. It should just write a linear amount. But I'll come back to the 8-bit per pixels later. Yeah, and then the scan lines it's set into 0. So all looks good. Great. Pardon me. Okay, so the next bit is a little bit scarier. We want to get the renderer working. So this probably is worth a little bit of explanation. This system, it's got a bunch of ways of getting graphics onto the screen. We've got a sprite system, a tile map system, for that kind of console ease and hardware acceleration. But we've also got access to linear video memory. And we're going to start with linear video memory because it's kind of the simplest. It's the hardest to work with as a developer for the console, but it's the easiest for us to implement. So we're going to start there. Essentially, there's a block of memory, a frame buffer, reserved into which we can poke bytes, and they get represented on the screen. And I talked earlier about the palettes. Two of these modes are 8 bits per pixel, so 1 byte per pixel. 2 of these modes are 4 bits per pixel, and that's 2 pixels per byte. So the low byte, high byte both contain a pixel. That pixel is an index into a palette, and that pardon me, that then tells a video chip, as it were, to render that colour in that location. So we map the memory onto the canvas, basically. The memory gets mapped into this square. Not much different to a bitmap graphic. If you go and mess with the bytes underneath the canvas, you can mess with the bytes. Can't quite remember how, but I did that with Wolfenstein. I wanted to do it old school when I did my F-sharp Wolfenstein. So you can poke around with bytes under the canvas. So same concept really, except we haven't got a lot of space in memory, so the resolutions are rather small. We could just use a canvas and write pixels to the canvas, and that'd be one way of doing it. But and the simplest way of doing it probably. But what I'd like to do is apply some kind of like special effects after we've done that. Like apply some CRT effects to the console so it can make it look a bit crappy and a bit blurry, and put some scan lines on maybe and stuff like that. And I did that in my Elite when I recreated Elite, the BBC, well, the 8-bit micro game came from the BBC, but the famous space trading game. I did a version of that of TypeScript, and I got some really cool shaders from the Shader Toy website, which did CRT effects, and I modified them a little bit to get them working as I needed. But I'd like to be able to apply those, and the best way to do that is in the GPU. So we're going to use WebGPU to do that. Why WebGPU and not WebGL? Traditionally, you'd use WebGL. It's slowly getting superseded by WebGPU, thank goodness, because WebGL is a really horrible API, as is OpenGL, to be honest. And it doesn't. Yeah, it's deeply unpleasant to work with. WebGPU I found a lot easier to work with. It's not supported in every browser yet, but it's in most. The latest version of Safari brought it into the mainline Safari release. It was in beta before that. It's in Chrome and Edge. I'm not sure about Firefox, but it's essentially the way this stuff's going, and it's a lot easier to work with. The code's a lot nicer. The shader language is improved. And you can do compute for it as well, which you couldn't really do for OpenGL without messing around. WebGL rather, without messing around. So we're going to use WebGPU, and let's look at the spec as to how this is going to work. I should say the other nice thing about WebGPU, it doesn't really matter for what we're doing, but when we get our memory array and want to translate it into pixels, the nice thing is we can just give that uint 8 array to the sort of sliced uint 8 array to the GPU, and on the GPU we can do all the unpacking to translate that to pixels on the screen, and it can just do all that in parallel. GPUs are so quick. So although I don't think performance is our key concern here, it's not going to hurt to save ourselves some CPU cycles and leave it to a GPU to do all the heavy lifting. So I'm going to go back to WebStorm, and you'll see I've pre-written this. It's a little bit more complex, but I'm basically same kind of thing. I should add as well, I mentioned at some point perhaps that maybe I hope to create a prompt template for various areas. For the dev tools, dev kit, where have I put it? Source. I've created a little prompt template which we can use, and we could preload this into all our Claudes. We'll see how we get on. I'm just basing my prompts around it at the moment, so I've taken, just wonder if I just need anything else from it. No, I don't. I'll take assembler out. Assembler doesn't matter for this thing. So I've written this spec for WebGPU, and I'm telling it to begin by reading those files. I'm giving some information on the shared array buffer, and this is one of the reasons we use the shared array buffer is we need to access it from a UI thread to put things on the screen. I pointed at the canvas. We're going to use request animation frame for this, which if you may or may not come across this before, depending on how much web work you've done. But essentially, it's a way of saying, give me the next kind of space that I can render graphics, and that will run at the same frequency as your display panel. So my monitor here is a 60 FPS monitor. It's a really nice monitor, but I bought it when buying a combination of higher frame rates and really good quality colours and things, and brightness was insanely expensive. Because I mostly code and don't game, I do game a little bit, but mostly code, I went for the quality rather than the frame rate. My MacBook's actual screen, it's a fairly recent MacBook, it's 120 hertz, so you get 120 frames a second through this. I want our rendering to always run at 60 frames per second, because the reason for that is that our CPU is freewheeling as it would in a real console, and if we run it at 120 frames per second or variable frame rates, if our video system were to pull the memory at more regular intervals, that's going to interfere with the timing that's happening on the CPU, or any timing that you do in your assembly code based around the 60 hertz display. So we're going to fix it to 60 FPS. I suspect the I'm going to make this clear actually. Yeah, so I'm that clearer, and hopefully the LM will pick up on that. So it's quite important because the timing is really critical on these old systems. Yeah, so that's that. It's going to capture the memory at each part, send it to WebGPU. I've asked it to focus just on mode 0 for now. We can update it later to look at the other modes. I've kind of explained the system. Yeah, I've explained that. I want it to be a nice pixelated view. I've given it a sort of nudge. Let's call that frame buffer rendering. I've tried to pull out the WebGPU bit from the frame buffer. And the reason I'm just trying to do that is I think later we'll want to put this in a public website, and we're probably going to make the web GPU and the console worker and things are going to be part of a pack that we pull aside from the React code. I don't really want it to be based entirely on React. So that's my spec for it. We'll see what happens. This might require a bit of work. I can well believe this goes a little bit wrong. Let's see how we get on. Check. I did commit, didn't I? So I definitely want to get a rollback point here. Let's tweak the spec. Okay. So I'm going to give Claude a new context. I want to exit, restart it, and then I'm going to say read /specs/ implementation /web GPU. I call it phase 1 because we'll do a phase 2, which is different modes and the special effects. But for now, we're just going to try and get something on the screen. That's probably a big enough task for a 1-hour episode. And I'm hoping it doesn't massively overspill. So fingers crossed that this goes well. I suspect it's going to come back with quite a few questions, but let's see. It may not. Okay, some questions. Okay, that's not too bad. I thought it would have more questions, so let's answer these questions. Let's do our normal approach to this. We'll just create a new... Oh, this is me working on that earlier. I started it over here. Okay, memory access. I should put it as for share memory buffer, should I? So it should be just use it. got use virtual console, I think, didn't we, in console integration. Let's have a look. Dev kit source console integration, and this has got the shared array buffer. Provider, and down here we should have a use virtual console. In there. We'll have it support the scanline palette map. There's no point passing the fixed palette up and down all the time to the GPU and on every render pass. It's fixed. The only thing we can change are the indexes into it. So I'm going to tell it to update that actually. Yeah, I shouldn't have said create a new one. That doesn't make a lot of sense in the context of what we're doing. Okay, so 4 questions. Let's poke them back into here. Let's see what happens. A bit of background on Web GPU. If you've not used it before, while this happens, I'm going to let it, do all the changes it wants. So we won't have to pay too much attention to it until it's done. When we see the Web GPU code, there should be 2 what are known as shaders, and shaders are the way you run programs on a GPU. And there's various types, but the 2 main types you use with graphics are vertex shaders and fragment shaders. Vertex shaders essentially set up the geometry. They process the geometry. In our case, we just want a square which fills that canvas. So that'd be 2 triangles essentially, and you essentially specify each point on the triangles. We can do it 2 ways. You can pass it in an array of points and then say index into the points. So you pass 4 points and then have 6 indexes. So 4 points of a rectangle, 2 triangles, make up a rectangle. So that would be 3 points of each triangle. You end up with sort of 6 indexes. You can do other little tricks as well to make these things smaller. Or you could just specify all the points individually. Normally you would pass that stuff into the GPU for what's called a buffer. I suspect because our geometry is so fixed, we just want this one thing always. It won't do that. I think it will just create the geometry inside the vertex shader, but we'll see. The other kind of shader you have is a fragment shader, and the fragment shader is what applies the colours across the rendered or the coordinates it calculates are required for the geometry. So normally, I phrase it that way because normally you pass it some coordinates of objects in 2D or 3D space, and you pass it a camera, and you pass it a matrix that tells it how to convert those coordinates into, for example, 3D space, an actual sort of eyeball space, perspective space. But we're not doing any of that because we don't need to. We really don't need to. We can just go with the sort of default coordinate system of the space, which is be 0 at the centre, and I forget which way the coordinates go y, but -1. Let's say -1 bottom, and 1 bottom left, 1 top right. We can just sit with that, and normally these things are converting it into the running this transformation. We're normally converting things into that space, but again, we've not got a variable camera or nothing like that, so we don't need to worry about it. I'm making a bunch of assumptions there. I don't actually know what it's written as code, but that's how I would probably approach it if I was writing it by hand. That's how I would probably approach it. So, some background. If this takes much longer, I will probably cut from here to there, so I don't have any more background to share at this point. That is the background until I see what it does. I haven't really thought about how I would implement the scanline palette switches. I guess I'd just send it over. I'd probably build a texture of all the palettes on, and then I send it those indexes with each, the scanline indexes of each frame with each render pass, and then just pick from the palettes. I think. I'm not sure because that might not work when you change paths. We'll probably have to, this won't be a done and dusted. We'll have to revisit this, but let's see what it's done. So test pattern.ts. I'm not sure quite what we did with that, but let's. Seems to be using it. Okay. So when it mounts, it's initializing a test pattern. Okay, well, let's see what's happened in. Oh, there's a few errors in here. Because it's not using it. What are the others? Navigator.gpu. What the heck's going on here? Oh, it's looking for a GPU on my Navigator. So yeah, okay. I'm not sure that's a good way of testing if that's supported. Okay, so I'll ask it to fix those issues. It's sort of repeated itself there, which is weird. I'm going to assume it's. Can you specify multiples for that? Probably not. Let's go into Claude. I'll see if it can resolve it for me. Let's see what it makes of those things. You're absolutely right. Okay, so it's got, I would have gone for pixelated, so okay. I agree, Rafi. Okay, and it's typing it, so hopefully that resolves the other issue. It probably would have run because I guess by the time it's actually compiled, it's in JavaScript land, it would work. But it's always nice not to see the red lines in WebStorm, particularly using the LLM because they can indicate bad things happening. That looks okay now. Memory's not used, so let's just take that out. Okay, that's that one. So that was good. Let's look at web GPU rendering. Okay. What's all? Okay, let's just grab some of these. I think it's problems with type, actually. think you have to add types for the web GPU stuff. Yeah, I think there's a type library you need to add, but I can't remember its name. Yeah, I think there's a types package you need. It's probably at types/web GPU, I guess, but I can't quite remember. These are things that you don't do once at the start of projects, and then if you do 3 projects of web GPU a year, you do it 3 times in a year, it exits your memory. It does mine anyway. There we go. I was almost right. At web GPU/types, not at types/web GPU. I was almost right, but glad I asked rather than just did it. Okay, it might just take WebStorm a minute to catch up with its all these changes. Okay, so got some errors down here. Line 318 doesn't look right. They're all the same. Okay, we'll have it resolve these memory issues. Yeah, I need to. Okay. Looking a bit healthier. Yeah, that's fine. It's not the end of the world. You can't do that, mate. Okay. Actually, I'll do this. Oops. So it's not used, I think. Yeah, okay. Stop. Okay, that's that one resolved. And then we've just got a where do we set the context? Go to a declaration. Ah. Okay. Is this in a sub method or something? Yeah. Okay. And then we put some unused imports, I guess. Oh, they're not needed. Okay, so clean up the file, just some basic nudges around it. Let's see if it works. Where's the shaders? Didn't see the shaders. Here we go. Right, so the shaders are often, you often see this when there's not many shaders in a system, where they just get embedded as TypeScript strings. You can pull them out and kind of get, again, I can never remember how to say this. I'm going to have to look at, say, Vita, Vitae, whatever it is. You could get it to treat them as blobs, as build time assets, and sort of just read them out of imports. This is okay for now, though. But so it's as I suspected. This is how I would have done it. It's setting it the geometry inside the vertex shader, rather than kind of passing it in, because there's no need to pass it in. And the fragments where all the actual work will happen, where it's going to get given the scan line map, the palette RAM, okay, frame buffer, okay, and it looks vaguely okay. Converting that to pixel coordinates. Okay, it's correct. It knows it's 4-bit per pixel. Nibble. It always makes me laugh. I'm sure Pooh Riley laughed at the word nibble the other day as well. Oh dear, oh dear. Ultimately what happens at the end of here is you return a colour. So this looks like it's fishing out from what I can see. I've not read it in massive detail, so I'm just going to give it a go. But it's finding the frame buffers, and it's then looking into the right palette index to find the actual final colour, and it's going to return the colour. And when you return the colour from the fragment shader, that sets it for that pixel, basically. All this stuff is the boring setup you have to do to use a GPU. And if you do something really simple, it seems like really overkill, but you can configure these things to do lots of interesting things, basically. Hence all these options. We've got something like Vulkan, which is like a desktop, sort of modern desktop GPU system. It's crazy. There's so many things you can configure. I guess that's its test pattern. Is its test pattern white? Let's look at its test pattern. Nope, it's just showing it as white. Maybe we need to run it to see it. Nope. Okay, let's just refresh. See if it's that. No, so the test pattern is just showing us all white. That does not look right because it's doing a flip. It should be doing a checkerboard. Look, that's not right. Okay, let's just ask it first before we dive into it. One thing we'll just do to make sure our pipeline's working before I ask it a question. Debugging shaders is a nightmare, to be honest, and debugging down into barrels of WebGPU is really awkward. What you find yourself doing in the end is using colours to indicate things quite often. So I'm just going to have this return a different colour. I want to have it red. So RGB alpha is what that is into a 4-float vector. If I go back to here now, right, red. So we know at least it's getting this far. There's no errors in the pipeline. It's rendering a colour, so it could either be this is wrong. I've just figured what might be wrong. The palette's set to, until we load the CPU, the palette's just on a default palette. If you recall, when we set up the palettes, we said, it'd be okay, it doesn't have to set the palettes. It doesn't have to set the memory until after it's started. If you remember, if we go back to the palette address, it's all 0 until we run it, and then it gets set. And it's not changing in here, which suggests it's still not quite right. But let's fix that first. Before we ask it a vague question, let's get the So we run the, do we press run? Can we have a memory space set up inside? Or is it just an artifact maybe? I think it might just be an artifact actually of the way the presentation system works. We need to take the snapshot. We just need to take the snapshot after, yeah, so it is set up because the CPU is instantiated. When the CPU is instantiated, it sets up a palette. So we just need to set up the snapshot. The snapshot's basically out of sync with the CPU. It's been caught before the CPU has started, I think is what's wrong. So we'll leave that for a minute. Okay, so go back to, we're not seeing a checkerboard test image. It's all white. I know the shader is running because if I hard code a red return color, we see all red. Let's let it out. Let's let it do some investigation based on the context it's got. And then we're going to have a quick peek around video memory. Ah, okay. I see the issue. I love its cheeriness. Like, imagine you're working on this, you wouldn't be, I mean, I'm not that excited. I'm like, stupid mistake I made. Awesome, I made a mistake. Okay, let's see what happens. Okay, we're seeing like an old TV scanline thing. That's pretty cool. That's what it's setting up. I didn't really look at it. If it's poked this into memory, our video memory starts at B00. Right, it's not poking into memory. It's just using a fancy trick. If we run it, let's see what happens. Does it go? Oh, there's no updates when we run it. Pause. Oh. No, okay, so it does look, it's updated. B00. Okay, that's the checkerboard. Okay. Let us, how's the checkerboard look again? Console. Okay, we can update our little memory filler, which is our original program, if you recall, to just write some colors. So it looks like we should have here, yeah, black. We've got 8 pixels of black, 8 pixels of white, 8 pixels of red. Okay, so we're reading that from a memory viewer. It's just how the views are getting synced is a little bit confusing, so we need to sort that out. But we can see if it's working by updating our memory viewer to write to screen RAM. So we want to write to a high byte of B0. We're going to write to the low byte of 00. That's our offset. We'll have it write a big long line of things. And we'll have it write the colour. AA is the word pattern. Let's have it write. I think 01. I think red is. What's red? Red is 2. Let's just have it write red colours of the top. I think that's right. If we run this, actually, so we've updated this, so it's going to write into screen memory, our address space here. If I assemble this, I guess I might have a problem with program counter and moved on. No, it's worked. Program counter is up. When we assemble it, it's actually program counter. Let me just, rather than go to not, because that could go anywhere, infinite loop, colon, jump to infinite loop. So we just want it to keep round and round and round, just going to jump to jump to jump to jump. Let's assemble that. We need to make these buttons press a bit, they don't press. There we go. Right, so we can write to screen memory. And the reason you probably can't see on YouTube, but there's a little pixel missing there. That's because I went to. I've not gone quite far enough. It's ending on the last byte, but because things roll around, we want to fill the byte. If we increment from 255 to 0, I should be able to just compare to this thing being 0. If I assemble that, yeah, it's filled the pixel in. So that's now gone 2 rows, so 128 bytes per row, and that's worked nicely. Now, I've no idea if this will work. We've come to a point where I want to run my crazy program. I said I've got something I prepared earlier. Let me just load this up. This may or may not work. We will see. It works. Sort of. It's a little bit rough. It mostly works. It's not quite right. That's not bad. We've got a smiley face. We have a smiley face on the screen. That's pretty cool, I think. We'll need to sort out why it's not quite right. There looks like some stuff in here not quite right. But we've got a smiley face. So here's the... I'm not proposing to walk people through this, but here's the code to draw a smiley face. Quite a lot of code to draw a smiley face. Wow, I'm pretty pleased with that. We have a smiley face. I mean, what more can you say? I've no idea why it's not quite right. We might have some error in our rendering logic. By the looks of it. But I like the way you can see it draw. So that's kind of like the old school, the old school 8 bits. It's not that fast. It's running at 3 megahertz. It's drawing a circle. That's quite complicated. Amazing. Great. How long have we been going? Can we try and fix a smiley face? We can have a quick go at fixing the smiley face. We've been going for 52 minutes, so we'll have a quick go at fixing the smiley face. And if it doesn't work, I'll cut it off, find out why it's not working, and we can talk about it next time. But let's have a quick go. Something we can do, and this is quite a useful trick. We can paste this into Claude. So we can go. We can do a bit of a screen capture. There we go. Screen capture. Yes, let's just capture screen. Am I capturing a screen or video? Can't remember how else I've set up. Capture such a portion. Capture. If I go to Claude, I'm going to say a smiley face. So I think the assembly's right because the horizontal line, you may not be able to see, but the horizontal line is missing a blue there, which makes me think there's something not quite right in how we're taking the bytes from our memory map and putting them into the GPU. Like we're occasionally just missing pixels. So I don't think there's anything wrong with the renderer because there could be something wrong with a horizontal line renderer, I think, but that seems unlikely that it would miss a pixel through that. That just seems very weird to me. But the missed pixels are always at the start and the end. They're always at the start because I think from memory I draw from there to there and from there to there. It's always a second pixel. Okay. The missing the second pixel on the line. So I can take the smiley face and I can pop that in Claude, and I can also I'm also going to say also C dot slash specs slash. It's not got the CPU implementation, but we can give it that. Path reference, we'll give it a path reference from the content root. Okay. It's assembly, isn't it? Yeah. So giving it the image, and I'm going to give it the assembly code as well. It's a lot of stuff I want to give it, but it should be okay. Where do I get the assembly code from? I get it from here. Okay. And we'll let it have a bit of a think about all of that. See how good it can be at diagnosing a fault. I'm swinging back to it being an issue in my horizontal line implementation. Yeah, there you go. Oh no, it's in the shader. It is in the shader. So it's backwards. Let's fix it. Cool. So yeah, it's in the shader. It's got some stuff backwards. So if things aren't even aligned in the right way in terms of you starting on the right bit, you know, if you think about where you need to start, odd even, it's starting the wrong bit. So let's refresh this. Let's paste in the Smiley, console, assemble. Oh, I need to run the console. There we go. Okay, so it was just an ever so slight way it was dealing with bits in the wrong order, meant that the start pixels weren't quite right. So we've managed to fix that fairly quickly. We now have a way to translate linear memory into our canvas using our indexed palette system. And we got there in an hour, which I think is pretty cool. Because writing the WebGPU setup code is always extremely tedious, boring, repetitive. It's horrible. It's horrible code. Like even WebGPU is much nicer than WebGL. It's still horrible to write. It's fiddly and awful. And I mean, it's necessary, but it's awful. And we've got there in an hour. I think that's super exciting. A bit of a crummy picture, but you know, it's a start, and we can start doing cool things now. Between now and next episode, I'm probably going to tidy the UI up a little bit, and some of these sort of sync issues, it's probably not worth watching me do that. If I find anything notable, we'll talk about it at the beginning of the next episode. And next episode, what will we move on to next? We could look at the debugger, making it debug code. We could do more work on the renderer. We could write some cooler demos. I'll have a think about where we go next. But you know, lots of exciting things to be doing. We've got the non-interactive bit out of the way, and we've got to the exciting stuff now. So thanks for watching. Stuck with me this far, and see you in the next episode.